Section 4.6, exponential and logarithmic models. So we've talked about exponential equations. We've talked about logarithmic equations. We've talked about the graphs of each of those. And we are going to move on to models, which means word problems. Okay. So I know word problems aren't always fun, but the nice thing is they kind of all fit into one category or another here in this particular case. Our first one that we're going to deal with is radioactive decay. And that's where substances break down over time because they are radioactive and they give off, I think, electrons, and then they break down into other substances and things like that. So a term that we need to know when we're talking about radioactive decay is half-life. And the half-life of a radioactive isotope is the time that it takes for half of the substance to decay. In other words, if you start out with 100 pounds of something and you go through one full half-life, you will get down to 50 pounds because half of it will be left because half of it has decayed. Then if you go through another full half-life, you'll get down to like 25 pounds because, again, half of what's left has decayed. And then if you go through another half-life, you'll be down to like 12.5 pounds because another half-life has gone by. So another half of what's left has decayed. So this is how a half-life works. And so it just keeps cutting things in half over time. So here's our first example. Bismuth-210 is an isotope that decays by about 13% each day. What is the half-life of bismuth-210? So things that decay, you can think of them as decaying continuously. So we can kind of use the PERT formula. Does that make sense? So I guess they didn't call it PERT. What did they call it? I can't even remember. But anyway, I'm going to give you a version of it. So we'll just say m of t equals m sub 0 times e to the RT power. Okay? And yeah. So this just means mass after a certain amount of time. So our initial mass, we don't even have an initial mass given to us. But the question is, what is the half-life? Right? So let's just pick an amount. How much do we want to start with? 20. Okay. And then after one half-life has gone by, how much will be left? 10. So the 20 is the starting amount right here. The 10 is how much is left after a certain amount of time. Then we're going to have the E. And here's the difference. Since it's decaying by 13%, our rate is negative. Does that make sense? It's not increasing by 13%, it's decaying by 13%. So we're going to put in for the R a negative, and then we put in our decimal 0.13, and we put in a T. Okay. Now, if we look at this, once we've written down this model, do we see that this is an exponential equation because the variable is in the exponent? So if that's the case, let's use our strategy for solving exponential equations. You remember what the first thing is that we always have to do? And I'll help us the first time. It's been over the weekend. We need to isolate first, right? So here's the base. Here's the exponent. We've got to get rid of the 20. How do we get rid of the 20? Divide both sides by 20. This is why it doesn't matter how much you start with, because once you do that first step, you're always going to have 0.5 over here. Right? If you started with 100 and you had 50 on the other side, when you divide, you're going to get 0.5. If you started with 2 and you have 1 on the other side, when you divide, you're going to get 0.5. So that's why it really doesn't matter what we start with when we're trying to just find the half-life. All right, so that was our first step, isolate. Then what do we do after we isolate? The base and the exponent. Yeah, in this case, especially because it's an E, we're going to take the natural log of both sides. And so we're going to have natural log of 0.5 equals, and remember what happens with these, they just cancel out, and we're going to have negative 0.13 times t left over. And then what else will we have to do here to figure out what t is? Yeah. divide by negative 0.13. And remember what this is. This is the amount of time it's going to take for 20 of whatever to become 10. So it's going to be the half-life. It's the amount of time. So if we grab our calculators and we take the natural log of 0.5 and we close our parentheses and divide by negative 0.13, we get 5.3. It looks like our units in this case are days, right? So 5.3 days is what I'm getting at least. So hopefully that's the right answer. Yeah, about 5 days. Okay, does that make sense how that problem worked? So the first part is you got to set up your equation, and it's going to be some sort of exponential or logarithmic, and then we solve, and that's going to give us our answer. So remember with exponentials, isolate, take the log of both sides, and then get your variable by itself. For logarithmic, rewrite it into exponential form, or isolate first, then rewrite it into exponential form, and then solve to get your variable by itself. So similar, but different processes there depending on which type we're working on. Does that make sense for this first example? Any questions before we go on? All right. Next one, cesium-137 has a half-life of about 30 years. If you begin with 20 milligrams of cesium-137, how much will remain after 30 years, after 60 years, and after 90 years? Well, this one doesn't even require us to do any what's the word I'm looking for? Doesn't require us to do any algebra-ish work, because they told us the half-life was 30 years, and I'm asking you about 30 years, 60 years, and 90 years, right? So if you're starting out at year 0 and you have 200 milligrams, after 30 years, if 30 is the half-life, how much will be left? 100, because that's how long it takes for half of it to decay, right? And then if we go to 60 years, how much will be left then? 50, because in 30 more years, another half will decay. And then if we go to 90 years, how much will be left? 25. So that is the whole deal with half-life, is that it is the amount of time that half of it goes away, that it takes for half of it to decay. All right. Does that make sense? That one was pretty easy, just based on making sure you understand what half-life means. Any questions on that before we go on? All right. Did I skip one, or is the next one 14, or example 4? Okay. So carbon-14 is a radioactive isotope that is present in organic materials and is commonly used for dating historical artifacts. Carbon-14 has a half-life of 5,730 years. If a bone fragment is found that contains 20% of its original carbon-14, how old is the bone? Well, we got the same sort of situation here, right? Now, here's what we know. We know the half-life. We know that there is a bone that has 20% of its original carbon-14 left. But we have to do some work here first, because we don't know the rate. Does that make sense? And we actually don't know the time. So we actually have to set up a couple different equations. The first one is we have to figure out what the rate is based on its half-life. So let's say we're going to find the half-life, or no, let's say we're going to find the rate, which we did earlier finding the half-life. We do the same sort of a thing. So let's say we start with, let's use your 20 again, and we're going to go down to 10. This time, though, we don't know the rate. We do know the half-life, which is 5,730 years. Does that make sense how this problem is kind of similar, except for last time we knew the rate and we didn't know the half-life? But it's still an exponential equation, right? So what should we do first? Divide by the 20 so that we can isolate it. And when we divide by the 20, we said that that's going to give us 0.5. And I'm going to switch these around just because it looks nicer algebraically if we write it this way. So then what are we going to do after that? Natural log of both sides. So this will be natural log of 0.5. This will cancel and we'll have 5,730 times R. Okay. And then what else do we have to do? Now these numbers tend to be fairly small, so we may have to use several decimal places. Let's take a look at what that gives us. Natural log of 0.5 divided by 5,730. Yeah, this is in fact, what I would do, this is a scientific notation number, and there's 3 zeros before you even get any actual numbers. So what I would say is let's just go ahead and leave it as this, because by the time we type it into a calculator, that's not that hard to type into a calculator. All right, so now let's go to the second part. How old is this bone if 20% of the amount is left? Now here's where I usually wouldn't go with a 20 and a 10, especially in a case like this. You could do whatever. But what I like to do is, anytime we're talking about percentages, I like to start with 100% because you're starting with all of it. So I would say if you ever have a percentage problem like this, start with 100%, and then they're telling us there's 20% left. So that way you're dealing with percent and percent. E, we know our rate is, what was it? Natural log of 0.5 divided by 5,730. And then times t. So at this point, again, where's your variable? Up in the exponent, right? So let's solve this and solve this exponential equation. What will we do first? Divide by 100. In this case, that gives us 0.2. Then what do we want to do? Take the natural log of both sides. So this cancels. We're going to have natural log of 0.2 equals natural log of 0.5 divided by 5,730 times t. Then what should we do? And you can do it in 2 steps or you can do it in 1 step. If you want to view this as a fraction, you can just multiply by the reciprocal. If you want to view this as natural log of 0.5 divided by 5,730, you can do it in 2 steps. You'd multiply first by 5,730 on this side to cancel that. And then you would divide by the natural log of 0.0. Yeah, that decimal point's in the wrong spot. 0.5 to cancel that. But do you see that either way, you're going to end up doing the same thing? Okay. And again, at this point, just be careful with your parentheses on these. Let's see what we get. 5,730 times natural log of 0.2 divided by natural log of 0.5. And it looks like we're getting about 13,300. If we think about an age that's this big, probably 13,300 years is a good approximation, even though it says 13,304.64798. And this actually leads us to, and if you're science teachers, hopefully they talk about this a little bit, but this leads us to some issues that we have with a process like this, carbon dating. Does anybody see any issues that might cause this number to be different than maybe what it actually should be in the problem? Like, did they? Here's one, it's even underlined. How do we know how much it originally had in it? Because we said there's 20% of what's left. Now we make an assumption. We make an assumption that the carbon content of the atmosphere is about the same now as it was then. So that's kind of how they do it. But we weren't back there 13,000 years ago to measure it, so we don't know for sure. The other thing is that these formulas are great as long as it's a closed system. So as long as, because a lot of times what they actually do is they compare the ratio of the radioactive substance to the what it breaks down into. But you have to know how much of that you had at the beginning too. So there's some assumptions that we make, and plus, notice how small this number was, right, when we put it into the calculator. Being off by just a little bit on this measurement is going to make it a lot different answer. That's why I said let's just use the exact value. If we had used that rounded off value like 0.0001 and put that in, we would have gotten a significantly different answer, probably several hundred years different, maybe not thousands. Let's actually check. So let's see. Natural log of 0.5 divided by, I think it was negative 0.0001. Wait. Oh, yeah, it was. So you know what answer I got? Oh, no, it was 0.2. No wonder. Okay, hang on. So 16,100 about. So that's 3,000 years difference, right? If I use the 1.2, that brings us to 13,400 approximately. So you have to be very accurate when you're dealing with things that are this precise. So just be aware of that when you see some of these things, that there are some things going on there. We can also talk about doubling time. So half-life, the amount of time for half of it to go away. Doubling time is the amount of time it takes for something to double. Okay, so if a quantity is growing, the doubling time will be at the amount of time that it takes for the quantity to double. A lot of times people will look at investments this way. Well, how long will it take me to double my money at a certain interest rate or a certain investment rate? And so let's take a look at this. It's going to be very similar. Unfortunately, this one's not quite as fun as doubling money. This is cancer cells doubling. So cancer cells sometimes increase exponentially. If a cancerous growth contained 300 cells last month and 360 cells this month, how long will it take for the number of cancer cells to double? Again, if it's exponential. So notice that in this case, we know the starting amount was 300 last month, right? The new amount this month is 360. We are saying that it's an exponential growth, and again, we kind of make the assumption these things grow in nature, they grow continuously, not just like all of a sudden it gets compounded like artificially at a bank. So we don't know what the rate is, but we know the amount of time was, let's just say 1 month. We'll just go by months this time. Okay, so our time is 1 month. And notice we've got to figure out the rate first so that then we can figure out the amount of doubling time. Does that make sense? Like we did with the half-life problem. So again, it's exponential. What are we going to do first? Divide by 300. Now I would reduce, but I'd probably leave this as a fraction because I don't think it comes out that nicely. Maybe it does. So if we divide by, let's see, cancel that. Is it 1.2? Okay, so it does come out nicely. And notice 1 times r is just r. So then what do we do to find our answer on this one? Take the natural log of both sides. And this is, again, a case where I might just leave my answer in exact form, natural log of 1.2, because otherwise you're just going to write down a bunch of decimals anyway. So that's Now what that means is we can go ahead and we can go to the 300 if we want to use that as our starting point still. We know that our rate is natural log of 1.2, and we're trying to figure out how long it will take to double. If you're starting with 300, how much will you have if it doubles? 600, right? And again, it doesn't really matter what we start with, because what's our first step going to be? Divide by 300, and if we're doubling, when we do that, this is automatically going to be a 2. Whoops. Okay. Then what should we do? Yeah, it gets kind of repetitive, right? It's nice because it's easy, but it gets a little bit repetitive. So natural log of 2 equals natural log of 1.2 times t. And we've got one more step. We're going to divide by natural log of 1.2. So again, calculator, parentheses are important. So natural log of 2 divided by natural log of 1.2. And it looks like we're going to get about 3.8 months. Okay. And again, depending on how precise, 4 months might be close enough. Although if it's Cancer, I'd kind of want to be pretty precise, but who knows? Okay. So 3.8 months is our answer there. Any questions on that? All right. Let's go on to example 6. Use of a new social networking website has been growing exponentially, with the number of new members doubling every 5 months. If the site currently has 120,000 users and this trend continues, how many users will the site have after 1 year? So once again, we're going to have to figure out the rate, but this time we know the doubling time. So let's take a look. What should we put down as our starting amount? $120,000. They're saying it currently has, and we view that just currently has this many. E. And what are we going to put in as our time to help us with this? We know the rate. We don't know the rate. But what are we going to put in as our time? And you have to be careful here because there's actually 2 questions, and we need to answer the first one first. The 5 months. We have to answer that question of 5 months because what did they tell us about the 5 months? It doubles. So what are we going to have over here on the left-hand side after 5 months? Yep, 240,000. Okay. Now we want to solve to figure out what the rate is so that we can figure out the second part of the question. So what do we have to do to start solving this? And again, it is exponential because the variable is in the exponent. What do we do first? Yep, divide. And no surprise here, when we divide, we're going to get 2. Then what do we do? Natural log of both sides. So that is going to cancel. We're going to have natural log of 2 equals 5r, and we divide by 5. And again, in this case, I'm going to leave that exact. So now we can go back and we can look at this and we can put in our 120,000. E, we know the rate is now natural log of 2 over 5. Here's where we do have to be a little bit careful. What are we going to put in as the amount of time now for the second part of the question? A year. But what's the problem with putting in a 1? Yeah, our units that we were using when we found out the rate was months. So if I'm going to put in 1 year, what do I actually have to write down? 12. And then that will give us our new amount. We'll just call it n. And at this time, there's nothing to solve. You just type it into a calculator. Now, the one thing I will say is you do have to be careful to put your parentheses in the right spot. The calculator will put parentheses after the e to a power. You just have to make sure you don't close both sets of parentheses until the end. Okay, so there's going to be lots of parentheses here, actually. Let me show you what happens. Let me see. I think I've got my calculator up here. All right, so when we're looking at this and we turn this on, and whether you have a scientific calculator or a graphing calculator, it's pretty much the same. We're going to put in the 120,000, and then we're going to go second ln to get the e to a power. Oh, this one looks different. Okay, so yours probably has parentheses, so I'm going to go ahead and put in the parentheses. So it's going to look like this. It's going to look like parentheses, and we're going to type in natural log of 2, and then close the parentheses, divided by 5, and then times, what was that number? 12. And then we finally close the parentheses for our exponent. Okay. And that may look confusing because a lot of times we look at it and we're like, oh, I should do 5 times 12 first and make that a 60. But remember, the calculator does order of operations. So it will do left to right. So it's going to do natural log of 2, and then divide by 5, and then multiply by 12, and then finally do e to that power. So that's how you need to do it. If you could put in extra parentheses if you wanted to. You could put in a parentheses, another set of parentheses right here. Whoops, what did I just do? Parentheses. Yeah, like that. You could put in, you could do that. You could put parentheses around your fraction if you wanted to, but you really don't have to. But either way, we get, looks like 633,363. So again, if we're looking at that, there's probably some rounding that we could do. 633,000 users is what I've got as my answer, but just some rounding off there when you're dealing with numbers that are that big. Any questions on how we solve that or how you put it into your calculator? Were all of you able to get that answer? Okay. Earthquakes. For an earthquake with seismic moment S, that's evidently a term that you know about if you were talking about earthquakes, a measurement of Earth movement, the MMS value, or the magnitude of the earthquake, is m equals 2/3 times the log of S divided by S sub 0, where S sub 0 is 10 raised to the 16th power. Does yours say to the 16th power? That seems like it might be a typo. Let me just double check. I want to make sure it's not like a negative 16 or something. What is this, 4/6? Nope, that's right. Okay. All right. So NS sub 0 basically is kind of a baseline measurement because the Earth always has vibrations going on, right? Because we're moving through space, it's rotating on its axis, revolving around the sun, all this stuff. So there's always some movement going on there, and so they've got that amount of movement that is just considered normal. And then the S means that there's some sort of additional movement involved. So that's why they always take it and divide out the 10 to the 16th. So let's take a look at this example. If one earthquake has an a MMS magnitude of 6 and the other has a magnitude of 8, how much more powerful in terms of Earth movement is the second earthquake? So what we do is we have to figure out each of these individually using our formula up here. So for the first one, we would have m equals 2/3 log. Oh wait, our magnitude is the m, so we need to put in the 8 or the 6 there. 2/3 log of capital S over S sub 0. And I'm going to leave the S sub 0 as S sub 0 for now, and I think it's going to go away, but we'll find out. What do we have to do? If we're trying to get this S right here by itself, what do we have to do first? Because this is now a logarithmic equation, right? So what do we do first? Yeah, or multiply by 3/2, right? Can multiply by the reciprocal. We've got to isolate it first. And 3/2 times 6 is going to be 9. And then what, do you remember what our main step was for logarithmic equations? We want to rewrite it into exponential form. So how could we rewrite this one? 10. I just gave it away to the 9th power equals S over S sub 0. And if we're trying to get this S by itself, we're going to multiply by S sub 0, correct? So that is the first earthquake that has a magnitude of 6. We're going to do the same exact steps with the magnitude of 8 earthquake. Okay, and first step again is multiply by 3/2. That would give us 12. Then what? I did the last one. You guys can help me this time. Yeah, rewrite it in exponential form. And so how would we do that? And again, since we're trying to get that S by itself, we're going to multiply by S sub 0. Since S sub 0 is a constant, it's the same value all the time. Here's what's going to end up happening. How much more powerful in terms of Earth movement is the second earthquake? Well, when they say how much more powerful, a lot of times they mean how many times more powerful is it? So we're just going to take the bigger one and divide by the smaller one. So the bigger one is obviously the second one, right? And we're dividing by the first one. And notice the S sub 0s just cancel out. So if we're asking how many times more powerful one is, we can just cancel those out. And then what do we have left here? What is 10 to the 12th divided by 10 to the 9th? 10 to the 3rd. Your rules of exponents say you subtract, right? Which means the second earthquake, even though the magnitude was an 8 compared to a 6, had 1,000 times more Earth movement than the first one did. Okay. Does that make sense? That's why these scales can be, the scales are nice because we can deal with the numbers a little bit easier, because otherwise the numbers are so huge. But we kind of lose track of how much more powerful one is than the other. So just by going up 2 there, it's 1,000 times more powerful. All right, so you've got some word problems there to work on. And again, they give you some of those equations. If they don't give them to you, you should have them in your notes now. And yeah, that'll be that. So those 6 questions. Tomorrow will be a work day. Monday, after we come back from our break, we'll plan on having a work day for the review. And then Tuesday, I better double check my calendar, but I think then Tuesday we'll go over the review and our test will be on Wednesday.